So, welcome back to the class on testing. So, we have been discussing memory testing and I have mentioned to you that there are several types of memories today and we have talked about embedded memories. So, an embedded memory is part of a system on a chip. So, today it is possible to integrate the CPU or the microprocessor. Sometimes we also have microcontrollers and maybe even DSPs. So, this is what we call as a multi-core design. Many processors may be integrated into the same chip. In addition to that, there may be memory cores. These are the embedded processors and these are the embedded memories. And the memories can be of different types, right? We can have flash memories. For example, in a microcontroller based system, the flash memory stores the program that the embedded system must execute. So, this is a non-volatile memory, meaning that it will not lose its contents when you power it off. We also frequently integrate SRAMs and DRAMs. These are read-write memories. We may also integrate ROMs or read-only memories for storing tables, for storing tables and the boot code and things like that. And we have talked about 2D organization of memories. And we talked about various memory test algorithms. In particular, we spend time on March algorithms, which are frequently used in the industry. Okay. These are linear time algorithms. Meaning the number of read or write operations is linear in the number of bits. So, that is the advantage of these memory test algorithms, but as I mentioned to you, the number of bits n is now very large. So, even the linear time algorithms do take quite a bit of time. To make matters worse, there are many modern applications that call for huge amount of memory. For example, your machine learning applications, right, or neural nets. These are very memory intensive. And as a result, people may have to think of alternate memory organizations. So, it is nowadays some companies are bringing out 3D memories. So, in these memories, as you can guess, the cells are organized in 3 dimensions. So, they may be made in 2D and then stacked. And interconnects between the layers is possible through what are called as through silicon vias. Okay. So, through silicon vias. You may have also heard about a term called as in-memory computing. So, what that means is, see, in the traditional way of building computers, we have a CPU and a memory, right. So, we have a CPU and we have a memory, and the CPU supplies addresses to the memory, reads instructions from the memory, then if necessary reads data from the same memory, then performs operations like addition, etc., and stores the results back. So, this is the way traditional uh, computers work. This is also called as von Neumann computing. It was proposed by the mathematician von Neumann, and we continue to use this architecture even to this day. But for applications which I mentioned like neural nets and so on, it may be better to use a slightly different architecture, and this in-memory computing is one such architecture where the sort of the bottleneck between the CPU and memory is being addressed by embedding computing inside the memory. So, this is sometimes called as the von Neumann bottleneck. So, what does that mean? See, the CPU is increasing in speed. Okay. But the memories may not be increasing in their speed. Memory speed does not increase at the same rate. So, fetching data or instructions from the memory or storing data back in the memory requires the CPU to slow down. So, people have tried to address this bottleneck, right. We do not want to use a very fast CPU and waste its time if the CPU has to work at the same speed as a slow memory. So, people have tried to find ways. For example, you may have heard about things like multi-threading. That is an example of how they try to address this bottleneck. There are also people who believe that it is better to embed the computing inside the memory, right. So, there will be computational elements that are inside the memory itself, which can perform the computations without having to create this kind of a bottleneck. So, instead of having one central processing unit which fetches instructions, data, etc., you can have these computational elements distributed inside the memory. So, these are ideal for applications like image processing or maybe even machine learning and so on. Okay. So, we will have to think of alternate ways to test such new architectures. Okay. The traditional memory test does not address these new methods of building computers such as in memory computing, etc. So, these are new trends that need research. I may have mentioned to you about ROM testing or testing of these non-volatile memories. So, in a ROM, the information does not change, it is programmed once and for all at the manufacturer's fab or the factory. So, the bits are always going to be the same. So, if you treat them as hexadecimal values, so this may be 4C, this may be 7, 8 and so on. So, a very simple way of testing ROMs is what is called as the checksum method. So, we treat these as numbers. So, 4C in hexadecimal can be treated as a number, 78 in hexadecimal can be treated as a number, and we can find the checksum, right. See, let us say any memory, we may not use all the locations, right. So, there may be some locations which are still available. So, let us say we have a few such locations. So, in these locations we could fill zeros. Suppose the 8-bit sum of all these locations happens to be let us say F7. When I add all these hexadecimal values and I only keep the last 8 bits, there will be overflow etc., but we are going to ignore those overflows and we are just going to truncate it to 8 bits. And let us say that truncated sum happens to be F7, right. So, in the last location we can store a value which is the negative of F7, okay. F7 is this number. So, what is the negative value of this F7? So, we will have to convert it to its 2's complement. So, 1 0 0 1 0 0 0 0. So, this is the negative value. Okay. So, we can store that here. So, let us say it is 09 hex. So, what did we do? The empty bytes that we did not want to use, there we stored zeros except in one location where we stored the negative sum. So, now if you go ahead and do the addition, you will realize that the sum will become 0. So, F7 plus 09, right, will be 0. ignore the carry. Okay. So, when you get this ROM, if you do calculate the checksum, that should be 0. So, if the checksum turns out to be 0, then we think it is all right. If it is not 0, that means there is fault. So, this is also a common way to apply testing procedure to ROMs. The other one is which I mentioned I believe in the last class. So, we can have a counter which reads out the contents of the ROM, and we compress or compact the responses using an MISR. So, response compaction. So, we will get a signature and that signature will be unique to each ROM. So, we can pre-calculate this signature through simulation, and if you do not get that signature, then obviously there is some bit error. Okay. So, even the checksum can be thought of as a checksum is also a form of response compaction. But a checksum may not be very reliable, because suppose you have this bit stored in one location and you have the next bit is this. See, suppose this bit changes to a 1 and this bit changes to a 0, right, because of a fault, then the checksum will not change, the checksum will remain the same. In comparison, the MISR based approach is more likely to find this bug. Okay. So, there is an advantage of using checksums, it is very simple. It can be even integrated in software. So, the checksum method, it is common to find this method in software. So, when you boot the machine, the checksum may be calculated to see whether the boot code has been tampered with, right. See, somebody may be intentionally trying to tamper with the boot code, etc. So, it is common to check the checksum before making any move. Okay. All right. So, we have looked at memory testing in some detail.